Can you see?
Okay,
yeah.
Good. So it's a pleasure to have Fran Globlek from CSUN, and he will be telling us about ABCDEFG of gauge and Painlevé. Take it away.
Oh, okay. Well, big thanks for having me here. It's so nice to be in this workshop. So I'm going to talk about this alphabet of gauge and Painlevé correspondence. So it's not going to be really that much in depth, just to sort of say some main ideas. So to start with, let me clarify what's the gauge part here. So specifically, we're considering four-dimensional n equals 2 star super young Mills with the gauge group G, and of course it's going to be one of the A to G simple Lie groups on a self-dual omega background. Okay, so we will certainly be interested in instantons. And there is another technical issue here that we, in this case, pass to the pure super young Mills limit. Okay, so we're decoupling the hyper, but this is not so important right now. So what do we have? Well, first, of course, the path integral localizes on the instantons. This is the classical Nekrasov story. And what we need to solve the theory is we need to integrate over the moduli space of instantons. This is perhaps a problem. So for classical Lie groups, we have the 8HM constructions. Whereas for exceptional ones, we don't really have a direct construction like that. There are some ways to go around it. There are some ways to say go from blow-up equations and look for some consistency. But in general, there's no direct approach. And I mean, what we're going to present also isn't a direct approach, but it is a new way to obtain these corrections. So once we have all of this, the solution schematically is the old story. There's a classical part, there's a one-loop determinant, and finally we have the whole instanton expansion. So these guys here, I don't know if you can see the mouse, is what we're interested in. We're interested in everything, of course. And once we have that, we can say extract the physics without the omega background using the standard Nekrasov conjecture. Okay, integrability. So we're sort of taking a step back. So this is a very old story about how the Seiberg-Witten solution is actually secretly, not so secretly, an integrable system. So this is the Donaghy-Witten integrable system. So there's a base being the Coulomb branch, whereas the fibers are the Jacobians of the Seiberg-Witten curves. So this indeed gives you all the ingredients to solve the theory. And in this sort of correspondence with integrability, the Seiberg-Witten curve corresponds to the spectral curve of the classical integrable system. Okay, so I won't go really into what all of this is, but it's relatively straightforward once we know what the integrable system is to get back to the physics. Okay, so in our case, starting with one adjoint hyper, it's going to be the elliptic Calogero-Moser on the Langlands dual group, which is an interesting thing observed by Kapustin as well. Okay, now we come to this big concept. Fabrizio was saying something about the tau function. So what's the tau function in integrability? It's something which generates the Hamiltonians. And it does it in this very specific sense. Basically, you take the derivative to get back the Hamiltonian. So think about, say, statistical physics and think about the canonical partition function and taking its derivative. This is more or less the idea, okay? So given this, you can notice for yourself that all of these Hamiltonians, if there's more of them, of course, they will have to commute between themselves. And in this particular case, this tau is simply the theta function of this Jacobian. So, I mean, given the Seiberg-Witten curve like this, we can use, say, Picard-Fuchs to obtain the prepotential. But we can do something else. So the thing we do here is we consider a particular lift of this integrable system. So it becomes sort of de-autonomized in a certain sense. What you can think about is turning on RG flow for parameters in the theory. Okay, so it's a very specific way that it evolves. Sorry. The simplest example here will lead to Painlevé 3, the 8. This is a particular specialization. So just y given on the, well, complex plane plus infinity, right? And these are just two parameters. So what's special about this? First of all, what's the Painlevé property? I'm giving you directly the answer here. It's a solution to an ODE which does not have movable branch cuts. Okay, so you can think for yourself, if you consider, say, solutions of ODEs, just the standard theorems of existence of solutions, how they're constructed and why this is a very crucial property. Okay, so they are quite rare. However, they are in a sense very ubiquitous because they tend to describe some say critical phenomena. Okay, and further, they're transcendent. So you cannot write a generic solution in terms of a known function. There are maybe some hypergeometric solutions, but in general, this is not so possible. You have to really fine tune. So what does this tell us? So there's this gauge Painlevé correspondence. So we used to look at integrable system to find out what's on the gauge part. But now we're going to be looking at this Painlevé side, and we're going to be searching for the gauge part there. So for SU2, this is quite well known, well, at least in some circles by now, that there is also a tau function for Painlevé 3, but it's no longer just the theta function. It's a Fourier transform of the entire path integral of the theory. So this is quite interesting on its own. This is called the dual Nekrasov-Okounkov function. So here we're not going into AGT. We're just sticking with this integrability viewpoint. Okay, and here's some more of the dictionary. There's some power of 2 missing here on purpose. So the point is that we have to just find and solve an ODE, and then we just plug in this expansion and get the full partition function. So this is what we did. So we looked at this for any of the alphabet Lie groups. So just a simple, not a product for now. What we get is a certain system of equations with generalized Painlevé to higher rank. There are multiple of these tau functions labeled by the center of the group, and they're related to each other by the shifts. So there are certain shifts we can make in the tau functions. We'll see an example right now after this slide. And what can we get from this? Just schematically, we can get the one-loop terms from certain functional equations if we just look at the lowest order terms. Okay, these are solved by Barnes G functions. This generalizes the usual Coleman-Mandula one-loop term. The instantons follow from recursion relations. Now, this is not on the blow-up. Okay, there are recursion relations for instantons, which are given in different omega backgrounds. This is not one of them. So this is interesting. And further, they're given by ratios of these one-loop determinants. So you can think about physically how to interpret that, perhaps. Again, no residue calculations needed. You just solve this ODE. It's very simple. Okay, example C3, SP3. This is complex, and you might find it as SP6 somewhere. This is the equation. It's not very pretty, but that's sort of an illusion as well. And basically, the claim is there are these two Y1 and Y2 here, and my claim is the following: that this is given by the appropriate Nekrasov-Okounkov dual partition function. Okay, as you can see, there's a certain shift here. Okay, the 1/2 that's a convention here about dealing with the root system. Okay, and of course it's not really this scary. I mean, it would be really bad if it were so scary. I just sort of expanded it to make it look like this. And also, again, exceptional groups are amenable to this approach. So E6, for instance, you can check up to 2 instanton. G2 you can check easily. With the rest, you perhaps might have some trouble, but you can check at least some aspects of this. And yeah, that will be more or less it. So there are some further topics, but you can go from here. So we're looking at this interpretation in terms of surface operators here. There's also an interesting connection to ABGN matrix models via the topological string spectral theory correspondence. And I have some results also about generalizing this to linear quivers, so products of all the groups. And yeah, also perhaps looking at some other backgrounds as well. And that would be more or less it. Thanks.
Okay, thank you very much, Fran. Are there any questions?
Hi, so I would have a question. So I don't quite understand, how do you obtain this Painlevé-like equation for different groups? Like,
well,
where do they come from?
The very short answer, I said there was an elliptic Avogadro Meeting, which you can formulate for any Lie group. Okay, so this one is going to be, I mean, more or less giving you some. This is work by Takasaki. If you want to check it out. So dealing with isomonodromy on the torus. Okay, so we're looking at the torus, but since there is no tau form of the equation of the torus, right? This is just this limit in which we're looking at it, at which we do find a tau form. So again, starting from the elliptic Avogadro Meeting, right? Yeah, and taking this in as a limit. Yeah.
Okay, thank you.
Okay.
Hi.
Yes?
Hi, thanks for the nice talk. It's Alma Gracia speaking.
Oh,
can I ask you one question? If you go back, you say that you can compute the instanton partition function starting from some recursion relation that you obtain via Painlevé equation, but that these are not blow-up equation.
Yes.
But I thought that from the work of Bernstein and others, it followed that Painlevé are essentially like blow-up equation. But now you're saying that this. So how is it that it isn't just a rewriting of blow-up, or it's just something?
Well, I mean, yeah, I mean, I know the work very well. So yes, I mean, so there's one thing, that work is just, I mean, is SU2. There are blow-up equations for any group as well, and this is something I want to check out as well. So I've been doing some rewritings and so on, and I'm not quite figured it out yet. But in general, yes, one should be obtainable from another, just sort of be a transform of one of the other, right? But I would say the blow-up equations give you the tau form, which then gives you a different set of recursion relations. So certainly there's this link, but I don't see it when I just look at one and the other set. They look fundamentally different, just, the equations.
Okay. And just one more question. If G is not SU2,
yes,
right, are the blow-up equation for this type of theory that you are looking at known?
Yes.
I see.
Yes.
Okay. Thank you.
Okay, very good. So if there are no more questions, let's thank Fran again for the nice talk, and we can